Hi, Assalamualaikum. Welcome back to my channel Physics from 5 KSSM. Today we continue 4.1 Force on Current Carrying Conductor in Magnetic Field, Part 2. In this video, I will discuss three learning standards. The first one describes the effect of current carrying coil in magnetic field. The second one describes working principle of a direct current motor. And the third one describes factors that affect the speed of rotation in an electric motor. For the first part, we want to discuss effect of current carrying coil in magnetic field. So this activity 4.4 is to observe the turning effect on current carrying coil in magnetic field. In my previous video, I will discuss about a straight wire conductor or a straight current carrying conductor. When placed in the magnetic field, will produce force that move the wire. So in this part, I will discuss about coil of wire. What happens when we place a coil that carry current in the magnetic field of permanent magnet? So you can see the coil here is coil ABCD. In this case, we want to observe what happens to the coil. Let's watch this video. So this is a coil of wire that connected to DC power supply or a dry cell. This is a coil placed in the magnetic field of permanent magnet. You can see the current flow from positive to negative. By using Fleming's left-hand rule, you can determine direction of force act on side AB and side CD. So for side AB and CD, when we use Fleming's left-hand rule, you will find that direction of force for AB is downwards, direction of force for CD is upwards. Why don't we discuss about BC? As you can see from here, direction of current for BC is parallel to the magnetic field of the permanent magnet. Thus, there will be no interaction between magnetic field of wire BC and magnetic field of permanent magnet. That's the reason why we don't take BC into discussion to determine direction of force, because there is no interaction of magnetic field for this part. We just discussed for AB and CD. So this one will produce one pair of force, same magnitude but opposite direction. So the pair of force will cause the coil to rotate. We add extra components to this coil like split ring commutator and carbon brushes. So this one will become basic structure for electric motor or DC motor. How can we explain the production of force or rotational force for this coil? The current carrying coil in magnetic field will rotate about axis of rotation. This rotation is due to a pair of forces of equal magnitude but in opposite direction acting on the side of the coil. The pair of forces actually produced by the interaction between current carrying coil and magnetic field of permanent magnet. Okay, the same situation as we discussed on a straight wire. Okay, the current carrying straight wire that placed in magnetic field. But in this case, it produced one pair of forces. That's the reason why the coil rotates. Let's try to sketch catapult field for this coil. So for this coil ABCD, you look at direction of current for AB is into the screen. For CD is out from the screen. By applying Fleming's left-hand rule, direction of force for AB is upwards, direction of current for CD is downwards. So this pair of forces will cause the coil to rotate in clockwise direction. This is axis of rotation, center part. Okay, let's try to look at the pattern of catapult field. For side AB, current is flowing in, so we use the symbol cross here. Draw concentric circle to represent magnetic field for the wire AB. Direction is clockwise. And then for side DC, current is flowing out, so we use dot. Draw magnetic field for the wire. Direction is anti-clockwise. Now let's look at what happens to the interaction between the magnetic field of permanent magnet and the coil. Above side AB or above wire AB, direction of magnetic fields are opposite. Thus, it will produce weak resultant magnetic field. For above wire DC here, same direction of magnetic field, so it will produce stronger resultant magnetic field. Look at the bottom part of wire AB, direction are the same, thus produce stronger magnetic field. Below the wire DC, direction are opposite, so produce weaker magnetic field. So what we do, how to draw the patterns? So we draw for the stronger magnetic field first. Okay, this is the line that you draw. Okay, so this part represents the stronger magnetic field. And then for the weaker part, you just add few lines and of course show less number of lines. Using Fleming's left-hand rule, for side AB, direction of force is upwards. For side DC, direction is downward. So you can see this is one pair of forces, same magnitude but opposite direction. So this pair of forces rotates the coil. The principle that we discussed about the turning effect of current carrying conductor in magnetic field, especially in this case coil. So this working principle is applied for direct current motor. So this is the picture of DC motor. As you can see, there is a commutator or split ring commutator. There is a carbon brushes, and then there is a power supply, which is direct current. The coil is placed in magnetic field of permanent magnet. So this basic structure for direct current motor. You can build a simple direct current motor by using copper wire, coil copper wire, and this is a large pepper pins. So you can just use this one so that you can place the copper wire, and then the copper wire easily to rotate, and then connect to DC power supply. Okay, let's watch this video, what happens to the current carrying coil in magnetic field. When the switch is on, you can see the motor or the coil rotates. The turning effect of the current carrying coil in magnetic field will cause the coil to rotate at axis of rotation. Direction of force, as we discussed before, determined by Fleming's left-hand rule. For this case, it will rotate in clockwise direction. Direction of rotation will be reversed if direction of current is reversed. Okay. You also can look at what happens to this coil of wire. When the switch is on, you can see the copper coil keep rotating until you switch off the current. So this is also apply the same principle as a DC motor. Now let's discuss further on working principle of DC motor. So this is the basic structure for DC motor. This is a coil ABCD placed in the magnetic field of permanent magnet. You can see the coil is attached to split ring commutator, blue color and red color, just to differentiate. And then this is carbon brushes loosely attached to the commutator. When the coil rotates, the commutator will rotate together with the coil, but does not fixedly attach to carbon brush. Okay, carbon brush X is in contact with red half of commutator. So we discussed about first half rotation when the wire ABCD is at horizontal. Direction of current in the coil is ABCD. Okay. Carbon brush Y in contact is blue half of commutator. Direction of current is A to B, B to C, and C to D. Side AB, force act downwards. You can apply Fleming's left-hand rule here. Side CD, force act upwards. So this one will cause the coil to rotate in anti-clockwise direction. For the next second half rotation, the coil is at horizontal again. Let's look at what happens to the carbon brush X and Y. Now carbon brush X contact with blue half of the commutator, and Y now in contact with red half of the commutator. You look at direction of current, D to C, C to B, and B to A. As we can see from here, direction is DCBA, which is opposite direction compared to the first half rotation. Now we check direction of force. For side AB, direction of force is upwards. For CD is downwards. So what happens to the rotation? The coil rotates in the same direction as the first half rotation. That's the function of commutator, that reverse direction every half cycle so that the motor will rotate or continue rotating in the same direction. Then only the motor, we can say, at normal function. Keep rotating in the same direction. How about the speed of rotation? What are factors that affect speed of rotation? So for this activity, we have a simple DC motor. We can use copper wire coil, a large paper clip. So what happens when the switch is on? Just now we already observed the video on this. So it will keep rotating until you switch off the DC power supply. For the combined magnetic field, this is one example of combined magnetic field or catapult field. Catapult field produce pushes at the left side upwards and the right side downwards. So this one will cause the coil to rotate. So what are the factors that affect the turning force? So we have three factors here: increasing the strength of magnetic field, increasing the current in the coil, increasing the number of turns in the coil. Increasing the force that produced on the coil, meaning increasing the speed of rotation. Or we can say in this case, the speed of rotation of electric motor depends on strength of magnetic field, current in the coil, and number of turns in the coil. Let's discuss some questions. What is the relationship between current in the coil and voltage supplied? When voltage supply increase, current in the coil increase. Describe the change in speed of rotation of the motor when voltage increase. The speed of rotation increase. Because when voltage increase, current increase, thus force of rotation also increase. When strength of magnetic field increase, it will produce greater force of rotation. The speed also increase. When number of turns of coil increase, this is also increases the force of rotation, thus increase the speed of rotation of the motor. So from here we can conclude there are three factors that affect speed of rotation: current, flow in the coil, strength of magnet, and number of turns of the coil. You look at activity 4.7 to study the direct current motor found in used devices and identify arrangement of the coil and commutator. You can go back and try to find any used devices and try to look at the component of the electric motor. So this one can be one of your activity as PBL. You can prepare a brief report and compare and contrast arrangement of coil, magnet, and commutator in DC motor. For electric motors which do not have commutator and carbon brushes, we have brushless motor and brush motor. So this is brushless motor and this is brush motor, the components. So what are advantages of using brushless motor as compared to brush motor? Let's look at the comparison between brushless motor and brush motor. The similarities between brushless motor and brush motor are both has magnet and a coil. This is a compulsory component required and uses magnetic force to produce rotation. Differences: for brushless motor, the coil is stationary but magnet rotates. For brush motor, the magnet is stationary, the coil rotates. The second one, for brushless motor, no carbon brushes, therefore no friction between the brushes and the commutator. For the brush motor, there will be friction between the carbon brush and the commutator, causes the carbon brush to wear out. So we need to replace it after some time. No sparking at commutator for brushless motor. And then for brush motor, of course, due to friction, it will produce sparking. This one will decrease the efficiency of the motor because some of the electrical energy supplied is converted to heat energy and light energy. For the brushless motor, because of no friction, it will operate at soft sound, or we can say soft operational sound. Does not produce noise. For the brush motor, due to friction, sometimes the machine that using this motor will produce louder operational noise. So you can study more on the advantages of brushless motor as compared to brush motor. So this activity 4.8 is one activity that will become PBD or classroom-based assessment on TP5. Explain the working principle of brushless motor. Write in table form the advantages of brushless motor as compared to brush motor. You can go and search more extra information on this. And then we have activity 4.9. This one will become project-based learning. What you should do is in group, you need to design a simple and efficient homopolar motor. Materials: neodymium magnet, AA dry cell and copper wire, SWG 18 to 22. What you do, gather information on homopolar motors from the aspect of working principle, shape and size of neodymium magnet, various design of copper wire that can be tried out. You can use the KWL data strategy form, and then you need to follow the instruction given here. And then present the outcome. Now we discuss formative practice 4.1. Number 1, with the aid of label diagram, explain the meaning of catapult field. So this is the diagram that used to explain catapult field. A catapult field is a resultant magnetic field produced by interaction between magnetic field from a current carrying conductor with the magnetic field from permanent magnet. You can sketch a diagram like this to show the catapult field. Number 2, figure 4.15 shows arrangement of apparatus to study effect of force on current carrying conductor. What is direction of current in the copper wire XY when the switch of the DC power supply is turned on? Okay, current flow from positive to negative, thus it will flow from X to Y. Explain the motion of copper wire XY and state direction of motion. The current in copper wire XY produces magnetic field that superimpose with the magnetic field from the permanent magnet, meaning interact. The two magnetic fields combine to produce catapult magnetic field. The catapult magnetic field exerts a force on wire XY and move the wire. Direction of the wire XY is to the right. So here you can apply Fleming's left-hand rule to determine direction. State three factors that affect speed of rotation. We have discussed earlier current in the coil, number of turns of the coil, and strength of magnetic field. Compare and contrast the structure of brush motor with brushless motor. Both consist of coil and permanent magnets. For brush motor, permanent magnet is stationary while the coil rotates. Brushless motor, the coil is stationary while the magnet rotates. State two advantages of brushless motor compared to brush motor: lower level of operational sound and lower maintenance costs. So the brushless motor actually is more efficient compared to brush motor. Okay, that's all my video today. Thank you for watching. Bye.